Dr. Martin Greenwald. Dr. Greenwald is the Deputy Director of MIT's Plasma Science and Fusion Center. He's a Senior Research Scientist and Head of Physics for the SPARC project. SPARC is a compact, high-field deuterium-tritium burning tokamak, currently under design by a team from the Massachusetts Institute of Technology and the recent fusion startup, Commonwealth Fusion Systems. Dr. Greenwald is one of the CFS co-founders and is past chair of the Federal Advisory Committee for Fusion Sciences and has served on many program advisory committees, working groups, visiting committees, and the U.S. Department of Energy review committees. And he is also an associate editor of the journal Physics of Plasmas. I'm really looking forward to his talk on high magnetic field path to fusion energy. If you have any questions, please enter them in the chat field and I will read them at the end. And also please be aware that today's talk is being recorded. So if you're uncomfortable with that, please log off. And also it is an unclassified meeting with external and foreign nationals, so please be aware of that as well. Otherwise, enjoy today's seminar, and I'll pass it over to you, Dr. Greenwald.
Okay, thank you very much, and thanks for the opportunity to talk about our work. So I want to acknowledge the team. I think the key thing here is that we come in two different flavors, at least. Of course, the people from MIT, the Plasma Science and Fusion Center, and some collaborating institutions, but also from Commonwealth Fusion Systems, which is a private company that actually funds the work that I'm going to talk about. So I'll start by giving a quick introduction to fusion energy, magnetic confinement. Now I see a lot of familiar faces in the grid. Good to see some people I haven't seen for a while because of the virus, but we'll go through things to try to bring everybody up to speed, then talk about the opportunities afforded by the new technology of high temperature superconductors. Spend most of my time talking about our plans and the physics for the SPARC device. And if there's time at the end, I'll say a few words about the role of private industry in the fusion program. And here you can see a engineering drawing of the SPARC device as it currently is imagined. Okay, so I think everybody would agree we need safe, clean, carbon-free energy. We're worried about global warming. We're worried about pollution. The question to us is, can fusion contribute to the solution? And that's not an obvious question. We're working on it, but it's a challenging problem. We know that we've been working on it a long time. There's a plasma physics question about actually making the very hot plasmas that we need, about dealing with the plasma material interface, and then harnessing the energy. So plenty of technical challenges. What we're talking about is deuterium-tritium fusion, where we have a hot plasma up to a couple 100 million degrees. And in that plasma, deuterium and tritium will fuse. One of their products is helium nucleus. It's charged, so it stays confined by the magnetic fields, gives up its energy, and sustains the reaction. The other fusion product is a neutron. It escapes the magnetic field, finds its way into a breeding blanket which surrounds the plasma, and there it undergoes a second nuclear reaction with lithium that recovers the tritium that we need, makes another helium, and then we recycle the tritium in the plant. So the net effect is to put deuterium and lithium into your device, recycle tritium and neutrons, and what you get out is energy, heat for electricity generation, or helium rather. And then once you got that working, it's a very conventional approach, for example, to make electricity through a standard thermal cycle, or you can just use the heat for some kind of process that requires process energy, like making concrete in the goal of decarbonizing industry. We know this is a difficult problem, requires high temperatures because fusion is a product of the strong, really it's mediated by the strong nuclear force with a very short range. So the nuclei that fuse are going to have significant wave function overlap. And since they're charged, that means that they have to have a lot of energy to get that close. And that can be seen here in these standard cross sections. But what you see is that the Coulomb scattering cross section is always larger, usually by a significant amount, than the fusion cross section, so that the nuclei are much more likely to scatter than to fuse, so they're going to rapidly thermalize and equilibrate. So instead of colliding beams, we need to confine hot plasmas for many collision times. Now to do that, we have to isolate and insulate this hot plasma from ordinary matter. In our case, we do that with magnetic fields. Again, pretty straightforward process. The charged particles spiral around field lines and therefore can't move off them in a perpendicular direction if they're long and straight and uniform. That works really well if that were the geometry. Important thing to realize is that the quality of the magnetic insulation increases with the strength of the magnetic field. That's because the gyroradii get smaller. That's gonna be important later on in this story. Now, of course, we can't just have a long straight solenoid because the ions are moving so fast, about 1,000 kilometers per second, and they take about 25 seconds on the average to fuse. So obviously you can't make a device 25,000 kilometers long. So you have to eliminate the ends. And we do that by wrapping the field lines around in a torus. You can see a picture here. And you also need a colloidal field for it turns out, to actually do the confinement as well. But you end up with these helically shaped fields wrapped around a torus. And it's not an accident that it's a torus. You'll see this is typical of magnetic confinement devices. Turns out there's a topological theorem where you can show that it's the only shape in 3 dimensions where a non-singular vector field, that is the magnetic field, can be tangent to the surface everywhere. And that's what you need if you want to do confinement. If they leave the surface, then you're obviously not confining the particles. Now, in magnetic confinement, the tokamak is the leading concept. There are other ideas out there, and people are working on them actively, but this is the kind of configuration that's had the best success so far. And we have a very good metric for that. That's the Lawson criteria back from 1955, where the parameters n tau and t are necessary. Certain minima in both of those are needed. We've achieved the required n tau and the t individually, actually in the 70s and 80s, but we've not put them both together yet after all these decades. We have had tokamaks that have run with the deuterium tritium fuel, produced substantial amount of fusion power, up to 16 megawatts, but we have not reached the break-even point for fusion in any of these devices. And that's sort of shown here. We've built just a whole lot of tokamaks over the years, about 170. There's an enormous technical and scientific base. And using the triple product, that's n times tau times t, progress exceeded Moore's law for about 30 years, from the late 60s to the late 90s. And you can see that here as we're marching up toward the break-even point. Since then, we haven't put any points further up on this curve. We are building the ITER device, which should be running with DT in 2035, but that's still a long way away, even from today, after many years. And so you ask yourself, well, why did that happen? And it didn't happen because the physics was uncooperative. It really happened because progress slowed when the devices got big and expensive. It just took longer to build and more resources. And you can see that on the plot here. JET is the largest machine in the world. It's operating now, been operating since the 1980s, actually. Another machine in Japan is just starting its commissioning. I think its first plasma will be later this year, about the same size. ITER, which is truly enormous device, it came under agreement in 1985, but research still isn't scheduled to begin until about 2030, with PhD in 2035. And then the devices, the future devices as you head toward commercialization are farther off and even larger. This one, the European demo, that one's so big it doesn't even fit on the screen. So you get some idea. Well, if you ask the question, well, when I say slow, how do I measure slow? And one way is to use the uh, aspirations from the International Panel on Climate Change. And they say that in order to avoid a catastrophe in the world's climate, we need to have zero carbon emission by around 2060. And that new technologies, if they're going to contribute to that schedule, have to have their first plants online in the early 2030s and be deploying something on the order of 10 plants per year in the early 2040s. And obviously, fusion on the schedule of these big machines just isn't going to make it. So, well, what do we do? And one way to think about this problem, especially if you're trying to sell the idea to private investors, is you put the problem on a quad graph. And in this case, we have two axes. One is how fast and small and inexpensive the devices is, and the opposite of that is slow and big and expensive, and that certainly characterizes ITER. And the other is the confidence we have in the physics. Low confidence at the bottom, high confidence at the top. And we have a lot of confidence. We have a big database, so we're pretty sure that ITER, when it starts up, is going to work. But as we've seen, the time scale is really not favorable. At the same time, private companies have attracted a fair amount of money on small but riskier concepts. And these are small enough where they can be carried out with private funding and built quickly and turned over quickly. They've been innovative, but they are taking a leap into the unknown on the physics, and so far haven't shown the performance that's required. So we would put those in the lower right quadrant. They're fast and small, they're inexpensive relatively, but there's still lots of uncertainty in the physics. And if you look at where their performance is in this N tau T curve, they're still down here. And some of them have been in that kind of level for many years. So be a challenge for them. Well, if you're familiar with quad graphs, you always want to be in the upper right quadrant. But there's another thing we want to consider too before we talk about that, which is how you retire risk when you're bringing out a new technology. If you have to put a lot of resources before you retire the most critical risks, you're on curves like the one above here, where you put in most of your money, but you don't retire the risks until the end. And if you have to do it that way, you have to do it that way, but it's unfavorable. It's better if you can retire the risks early and at lower cost. That gives you, first of all, less investment in the beginning, and it also means you can be more agile if you run into problems. You can try other solutions. So with that together, those 2 points, we're looking for solutions that live up here. That's where breakthroughs are, where we can use the high confidence in the physics that we gathered and that we use for the design of ITER, but reduce the scale in order to learn fast and to retire risks quickly. And we actually think the basis for that breakthrough is here, and that is in high temperature superconductors. And the left-hand plot shows the critical temperature for superconductors as a function of date. And here's this big discontinuity when this new class of superconductors was discovered. It was a surprise. Won a Nobel Prize. It was the shortest time between a Nobel Prize and the discovery and a prize. When it was formed, though, it was really considered a laboratory curiosity. There's a little picture of the material in the lower right here. It was just some black crystals in a petri dish, and nobody really knew how you would turn that into a practical material for making a magnet or any kind of carrying any kind of current. But some people actually understood the implications. This is a publication by some colleagues of mine at MIT, was written in 1987, where they saw the potential. They didn't know how to do it, but they said, look, if you can make a wire out of these new materials, they're great for fusion. And it took the rest of us a bit more time to catch up, but it's a pretty, it's obviously a potential for harnessing this technology to our aims for making fusion energy. Well, what's happened is that technology is out of the lab and into industrial production. People work for years and years to figure out how to do this, and the way they did it, you can see over here on the right. They laid down a very, very thin layer, about 1 micron thick, of the compounds. These are rare earth barium copper oxides. That's the superconductor. And that's put on a very strong substrate. And in effect, what you get is a single crystal, a few millimeters wide and hundreds of meters long. And so that's how you go from these little crystals to a practical material. It shows up in the form of these ribbons you can see here. And a cross section, you see the strong steel core. There's a layer of the superconducting here, too small to actually see, and it's usually overcoated with copper or silver for practical reasons. And lots of people make this stuff now. You can just go out and buy it. And it's really ideal for the kind of large volume magnets that we want. Here you can see the properties of superconductors. The amount of current that you can put through a superconductor depends on temperature and the applied magnetic field. The parameter range that's accessible with a conventional low temperature superconductor like niobium tin is shown in this red volume, and it's expanded dramatically for the HDS superconductors. And importantly for us, it then allows you to run at very high fields, and that's the big win for fusion. It has some engineering advantages as well. And there's been dramatic progress in the magnets people have been able to build with this. This chart's a little bit out of date, but people have just marched up to high field. Here's an example of a magnet that our group was collaborated on. Maybe you can see the scale. That little scale in yellow is 10 centimeters, so it's quite a small magnet. But it reached 26 Tesla, all high temperature superconductor. And pretty dramatic. A conventional superconductor would be much, much larger. So why do we care about that for fusion? Well, at higher fields, fusion reactors can be smaller. We measure the size of a fusion device in gyroradii. So the size is really R over the Ein radius, which is proportional to the field times the size. If you dig into it a little deeper and you look at what we've learned, physics we've learned, the fusion reaction rate goes like b to the fourth, and the fusion gain goes like b cubed. And those are very strong exponents for any system. And the result is plotted on the right, where we plot contours of fusion gain versus size and magnetic field. That's a linear size. So of course the volume goes up as the third power, so very quickly. And the general shape of those curves comes from the simple arguments that I mentioned, but of course, actually getting the numbers and exact shapes did depend on years and years of theoretical computational research and experiments. But we have these curves now, so we know what kind of gain we're going to get when we build one of these devices. So what did that mean? Well, ITER was designed, one of its specification was to run at the highest field that you could get with the superconducting technology that was available. And what that means is using LTS magnets, the right-hand part of this curve is inaccessible. So ITER running at the highest field it could was still at a major radius of 6 meters, which sets the scale. It's an enormous machine. Basically, it's required the combined resources of the entire industrial world. And something like 50 years from the Reykjavik summit, where Gorbachev and Reagan decided to build the machine or proceed with the project, to DT operation, which is projected for 2035. And if you only can build 2 machines in a century, that's pretty slow progress. So with the high temperature superconductors, you can slide down that curve to smaller size. Here's, for example, a concept of a pilot plant that we've talked about, which would produce the same amount of power as ITER, but roughly 1/8 the volume. And what this superconductor does is it enables a whole new class of devices. And I want to make it clear, this is not a design, this is a concept for a class of modular reactors. And we use it to help guide research. What are the issues at this scale? It was actually originated in a graduate design class at MIT. And there's a number of interesting innovations, not just the high temperature superconductors, but probably not time to talk about that today. Well, we're not really ready technologically or economically to build a machine of that arc class. So instead, we're focusing now on SPARC. That's an intermediate step. We slide down the curve a bit farther to 12 Tesla. Turns out, you can use the same technology, same field at the coil for the SPARC magnet and the arc magnet. And you can still get pretty high gain. For people who are familiar with fusion, magnetic fusion, it's essentially a 12 Tesla version of the Aztec upgrade or the D3D Tokamaks that are currently operating, very much mid-scale devices. So we set ourselves a mission, and the mission is to make a plasma with robustly break-even gain, that is capital Q greater than 2. And that's sort of at long last the Kitty Hawk moment for fusion. Our hypothesis, was that this would be a sufficient demonstration to put fusion firmly into the national energy plans. And moreover, as a privately funded effort, it would attract the investments for the next step. We also wanted to demonstrate those magnets at scale and integrate it into a high performance plasma. And finally, provide the physics basis for the pathway. And so that means demonstrating high field, high gain scenarios. So that's the mission and our aspiration. What's the plan? Well, first of all, it's privately funded. We began officially March 2018. The notion is to bolster the research education at MIT while building this strong industrial entity, Commonwealth Fusion Systems, who has the ultimate aim to commercialize fusion energy. They've gone off and raised capital. They've raised about $215 million so far. So it's a pretty big effort, and about 240 people at last count working on it. So it's a pretty good team. The notion is with private funding, we can go fast, we can accept risks, we can learn from our mistakes. The federal government, as I think most of us know, is pretty risk averse at this point. And there's a different tolerance for risk with private industry. So that's important to how we do things. We've broken the project into 3 phases. Phase 1, we're almost finished with now. 2 parts to that, the R&D and demonstration of HDS fusion magnets at scale. The test of a, say, 2/3 scale model coil will happen, I think, June of this year. That's currently in its final assembly. And then we're doing the physics and the engineering design for the tokamak itself. When that's done, this early this summer, we'll begin phase 2. That's the construction and operation of the SPARC device. And following that is phase 3. CFS goes off and it builds, with hopes, the first fusion pilot plant, which would be in the ARC class. Now, that seems pretty audacious, right, for a startup that's 2 years, 3 years old and a university. But for those of you, again, who've been around, consider some history. In 1974, the fusion community got together and said the tokamak physics was mature enough to try a DT machine. Now, at that time, the most powerful machine that existed in the world was the ATC tokamak at Tokamak at Princeton Plasma Physics Lab. They were building PLT, but it was not operating yet. But the community felt confident enough that time to try DT. It was approved for construction in '76. They actually, I think, DOE probably waited till PLT turned on before they did the approval, but it was pretty fast. And then the machine itself was built, commissioned, and the first plasma was in 1982. So what we're saying is, okay, we think the HTS technology is mature enough in 2018 to go and build a tokamak from it. Now, this is a slide borrowed from Mike Bell. He gave an interesting talk a couple of years ago on the history of TFTR. And one of the things he pointed out was how big the extrapolation was in 1974 from operating tokamaks. And you can see here that it's orders of magnitude, 10, 100, 1,000 times, and things like fusion power, just, 100 million in what had ever been accomplished. And yet they took that on and checked off all those boxes. Here is the equivalent set of extrapolations that we're doing from current day, and you can see that those extrapolations are actually rather small by comparison. So where are we? We have this what we call SPARC V2. That's the starting point for detailed engineering. It's a 12 Tesla machine at 1.85 major radius. Again, the similar size to existing machines. That would allow us, though, to have 8.7 megamps. And we think that with 25 megawatts available for external heating, we can get fusion power in the range of 50 to 140 megawatts. I said that we built machines of that size. Here SPARC to scale with D3D and Aztec upgrade. Those are two machines that are running. There's about half a dozen others of that scale in the world that are running right now, and another 5 that are bigger. So again, this is quite in the middle of the range of machines that we know how to build and operate. So we think we know how to do that. There's some extrapolations in the engineering, but not as big a step as ITER is. What we tried to do, though, is to stay as much as possible within the ITER physics basis, using proven heating and control techniques. We tried to stay away from operational limits. So we run at lower beta, lower normalized density relative to the limit. We stayed away from regimes where there were complicated control systems required. We also kept the pulse. We're keeping the pulse short, even though the magnets are superconducting and will stay on steady state. There's engineering complications and nuclear complications when you go to very long pulse. So we just want the pulse long enough for the plasma to reach steady state. And again, keep within the nuclear envelope of fusion precedents, particularly TFTR and jet. We also wanted to leverage as much technology as possible. I won't go into the details here, but as much as possible, we're using technology that's already been tested, mostly in fusion, but some cases in other systems, and just adding one key innovation that's in the high field magnets. Okay, so how do we estimate fusion performance for a device like this? Well, there's no closed form solutions for turbulent transport. So we use a hierarchy. We start with 0D empirical scaling. We characterize the transport with a scalar confinement time. There's a big database that was assembled for ITER. So we'll just use the scaling that was developed for ITER. And I'll show you the results in a moment. We can also use dimensionless identity. Of course, physics equations can be cast in dimensionless form. So if you find that the appropriate two plasmas that have the identical dimensionless parameters, the relevant ones, the plasma physics should be identical. And it turns out there are such discharges, so we can use that to predict performance. We can also do time-dependent simulation. We can use quasi-linear transport models that are derived from more first principles models and a bunch of other physics, and actually calculate the time-dependent evolution of a plasma. And finally, we can compare it to nonlinear gyrokinetics, which is sort of the standard model for transport in magnetized plasmas. And we've done all of those so far. For 0D, we use a scaling law, characterize that as with an H factor, which is to say we don't enhance or degrade the confinement time by any calibration factor. And then we do a calculation in the density temperature plane. We can calculate the fusion rate, radiated power, then use the confinement law to calculate the input power required, power balance to calculate how much of that has to come from external heating. And if you do that for SPARC, this is the plot that you end up with. The operating space that we're interested in is in yellow. It's basically set by a number of limits. The red curve is Q equals 2. So we want to be above this line. So anything above this line is Q greater than 2. There's a threshold for confinement regime we want to be in. I can't go into the details here, but it says we need to be above the green line. So above here. We only want to pay for a limited amount of heating power, so we have to stay below the black line. That's the auxiliary power equals 25 megawatts. And we also set an engineering limit for the fusion power, and that's the cyan line, the blue line here. And that defines our operating space. And you can see we actually do considerably better using the ITER physics rules. We can get up to 11 Tesla, in this case, and 134 megawatts. Interesting to note that if we didn't have this administrative limit, we could actually go up to much higher powers. So we will have to control the plasma density otherwise, or the fuel mix, otherwise we'll create more fusion power than we can actually handle. We have lots of margin. If you look at, what happens if you arbitrarily put a factor in front of the empirical scaling, you can see that you stay above Q equals 2, which is this black line, over a very wide range in H factors. At the higher end, limited, as I mentioned, by the fusion power we can develop, and then at the lower end by the auxiliary power that we have. But we can exceed our mission fusion gain even with H of 0.7, which is really several standard deviations below the database. So that's all good. Well, what about dimensionless parameters? This is a set of interesting dimensionless parameters for plasma physics: beta, rho star, nu star. Also, we'll have the Q and the normalized density. And one thing you can see, I should mention the black points are the ITER database. That was where the points that were used for the scaling law. And you can see that we're at least as close to the data center as any of the ITER discharges, and actually closer in a number of parameters. But I think the more significant thing here is that you can find discharges, and here I've highlighted in red about 20 discharges from the jet tokamak, where you come very close to matching all of the plasma physics dimensionless parameters simultaneously, and also the geometric parameters as well, the shape of the plasma and the device. So we've essentially seen most of the core plasma physics in those jet discharges that we're going to see in SPARC. So then you might ask the question, well, why didn't those jet discharges generate 100 megawatts of fusion energy? Why aren't we done? And that's because fusion, of course, is nuclear physics. It doesn't scale with dimensionless plasma parameters. It cares about the temperature compared to the thresholds for nuclear cross sections. So this is a regime we're eagerly waiting for. I'm looking forward to seeing. Okay, well, we've also done time-dependent plasma simulations. These have now reached the level of maturity where they can just use basically all physics with no calibrations, really. If they calibrate of anything, it's really more basic first principles models, and they have a lot of physics in them. Won't go into here. But when you actually do those predictions, you get time histories of temperature, gain, fusion power, and other parameters. And interestingly, the results are remarkably close to what we get from empirical scaling. In fact, probably in this particular case, closer than the uncertainties in either. So this very, very close agreement is somewhat fortuitous, I'm sure. But they both predict more than 100 megawatts of fusion power and fusion gains in the order of 10. So that's promising. They predict, the kinds of temperature profiles that we might expect. Temperatures of the electrons and ions over 20 keV, slightly peaked density profiles. Again, what you might expect empirically from today's results. We've taken another step, which is we've done nonlinear simulations of the gyrokinetic turbulence. And part of the reason for this is because the quasi-linear models are calibrated against the gyrokinetics, the nonlinear gyrokinetics. But that was done in slightly different regimes. So we wanted to make sure that calibration was still valid. And the answer is that they are. And that there should be no surprises in the turbulence regimes that SPARC is in compared to other devices. We probably will take another step to launch a fully nonlinear gyrokinetic prediction of the profiles. This is somewhat a heroic simulation, so we're thinking hard before we do it. But that's where you constrain the gradients at each radii with fluxes that you calculate from the nonlinear gyrokinetics. And that would be a real first principles prediction of performance. Okay, well, you got to get power into one of these devices. We're using ICRF, just a single type of heating, no neutral beams, no ECH on SPARC. It's been proven to work on CMOD, for example, at the sort of densities we're going to operate, and on DT devices, TFTR and JET were also successful with ICRF. Probably used 120 megahertz. That has good options for heating in all deuterium plasmas. We would run with a hydrogen minority at 8 Tesla, and then at 12 Tesla with a helium-3 minority. You also get good heating. And you can see here in this plot, I hope the heating power is very well localized in the plasma core. So, and with very good single pass absorption. So that looks really, really favorable for heating. And we can calculate what the heating profiles of various processes look like. And again, it's very peaked on axis. We can calculate how much power goes into the electrons, into the ions, both from the ICRF and from the alpha particles in a fully developed fusion plasma. And actually, there's about twice as much power going into the electrons as into the ions. It turns out that transport tends to be dominated by ions. The electrons tend to lose their energy through radiation. So when the plasma leaves, it's leaving the plasma actually through the ion channel. Well, okay, you got to get the power in. You also got to get the power out. And this is a challenge really for all high performance devices. You start to do the scaling from up from today's machines, and you see that to get into the sort of regime you want to be in for a power plant or reactor, the first of all, the interaction of the hot plasma and ordinary matter is really a tough one. Um, and in particular, one of the things we worry about is that the heat flux footprint scales like 1 over the magnetic field, and that's shown in a well-known empirical result here and extended further by some, uh, extended further by some more recent, well, not recent data, but data that came somewhat after the original scaling from CMOD, extended it up to 1.2 Tesla. And you end up with very small scrape-off layers, very concentrated heat. There's some recent simulations which suggest it might get larger at low rho star, but we're not going to count on that. So we've got to deal with these very intense heat loads, and our basic strategy for that is to sweep the strike point. So this is a GIF that didn't animate, but you can imagine that the strike point is sweeping along these diverter surfaces. And if you do that, you get a heat load which oscillates, but the calculations show that it can, the material that we're going to use, which is going to be tungsten, can withstand those heat fluxes for fixed pulses. This is not a steady state solution, but we have other ideas for how you might do that. And we took fairly conservative assumptions about, for example, how much of the power would be radiated. And we think we can actually do better than that. People who know about tokamaks know we worry about disruptions. So we have to think about that for a machine like this. Well, one thing is we stay away from operating limits. That's a good thing. So we're far from the pressure and the density limits. So that should reduce the disruption probability. Disruption forces are not obviously more difficult for a compact high field device. You might think it, but it turns out that the I cross B and all the stresses are about the same. The distances are smaller, so the lever arm for mechanical forces are smaller. The actuators can operate more quickly, but quench times for the plasma current can be faster. So it looks like a wash. Runaway electrons, which is a real concern for disruption, it's a little bit less of a problem for a smaller compact device because the collisions and synchrotron radiation will provide more damping, and the exponential growth of the avalanche is a little bit less. But it's something that we would worry about. So we're actually, I guess I lied a little bit. Here's another innovation that we're going to be trying out to mitigate disruption runaways. Looks very promising, and we're actually working on this quite hard. There's some simulation work that I think people will hear about soon. It came from an original idea by Alan Boozer, and he's always looking for ways to use non-axisymmetric coils. And in this case, you put in a coil into the machine that couples the flux when there's a change in dI/dt, but it's not axisymmetric, and therefore creates non-axisymmetric fields, which break up the flux surfaces. Not something you want to do in steady state, but when there's a disruption, what that can lead to is very rapid loss of the seed electrons, which then can avalanche. And the Val Iso has done some nonlinear MHD simulations with Nimrod, and it really looks very promising. We're probably not going to use the n=3 coil that I showed here. That actually makes the geometry a little easier to see, but it seems like the n=1 coil works best. So this is going to be incorporated into the design of the machine, and we're very optimistic about it. Unfortunately, it's too late for ITER to incorporate something like this. So they have to they have some real challenges in mitigating this issue. We're going to produce a large population of fast alphas, so you have to think about their transport. First, from orbit losses, neoclassical and ripple transport. Well, SPARC's being designed with very, very low ripple. So if you, right out of the design, I'm showing the cross-section of the machine in black and the ripple contours. It's very, very low, 0.25% loss. So a fraction of even what's lost from neoclassical losses. And they only come from this very small population of alphas that are born at the edge. Most of the alphas are born in the center where it's hottest. We also look to see what happens if there's assembly error when you put the machine together. So we actually took a pretty conservative estimate of what the assembly errors might be. And when you do that, the ripple curves, which are shown here, go to these red and orange ones. And it looks a lot higher, but it turns out, again, the ripple losses are also only significant at the edge, and there the ripple is no larger. So in this case of really extreme assembly error, we only get 1% loss. So that all looks promising. We have to think about the interactions of fast alphas and MHD, and we've done some linear analysis of that, but this is actually one of the main physics reasons for doing this experiment. The fully self-consistent nonlinear interaction of the fast particle distribution in phase space and MHD in these plasmas, that's a cutting edge research problem. And there's some advanced models that are looking at this, but we really need a burning plasma experiment to validate. And if you look at the physics justification for ITER, this really shows up as the #1 justification. So it looks like our physics will be similar to what is expected on ITER. That's because the temperatures and temperature profiles will be similar. Turns out you can show that the drive and damping terms are similar if the temperatures are similar. People are fairly optimistic on ITER that at least in their normal operating regime, that the losses from high frequency MHD will not be too bad. We actually expect the higher field to push us to higher M and N numbers, which actually should make the transport of particles a little lower. But this is a key physics issue for us to look at. Okay, well, I've just touched on some of the physics. There's a lot more. There's a special issue was published at the end of last year, so there's a number of papers for people to look up if they want more information. Well, what's next? Well, the detailed engineering is underway. We're going through conceptual design reviews of key systems, taking a deeper dive into the physics validation. We expect the engineering and the physics to be reviewed in late spring or early summer, and that would lead to a ready for construction milestone and on or around June of this year. The site selection, actually, this is actually slightly out of date. I see we've actually announced the site. It will be at the former site of Fort Devens in Massachusetts. That's in the suburbs of Boston, commuting distance away. They've also secured the supply of tritium for the experiment and also the high temperature superconducting material for the material. And these are the two of the things in the supply chain that you might worry about for a machine of this type. And this is what the machine looks like. Again, this is not a cartoon. This is actually a rendering of the engineering design, at least as it was a few months ago. There's some small changes that have taken place since then. And I just wanted to say a few words to finish up just on private funding. Let me not talk about this. Just to note that, okay, CFS is part of a nascent fusion industry. There's quite a few of these companies now, and the list is growing. And so I'm talking to mostly people who are, I know, like I was, worked in the government-funded program for a long time. What does this mean? Well, the first thing I'd say is that this really serves as an indicator for the value of the fusion research. It's people are willing to open up their wallets and put money into it. And those of us who have worked in the field for a long time should be happy about this. This is what we want. This is how technology gets to market. We're tracking new stakeholders, energizing the public, building momentum, and it gives us some diversity of approaches, which is important. We know that fusion has a lot of potential, but it also has a lot of risk, and the diversity can help us mitigate some of that risk. And that is how new technologies get to market. In the U.S., the government isn't going to build power plants. So the question is, when do you make the pivot to private industry? And again, our hypothesis is that we're at the point where we're ready to start doing that. So, there's a role. The mandate for government and universities is basic research, and private industry to develop into a commercial product. So anyway, we think that's a good thing, promising for both sides, and holds a lot of promise for the future. So I can just leave that here. So thanks a lot for your attention.
Thank you very much. And I invite everybody to unmute yourself so we can give a nice applause.
This is the weirdest part of giving a talk remotely.
Yeah, we wish we could give you an applause live, but it seems like a lot of people enjoyed your talk, and I did. And there are already lots of questions, so I'll start reading them. From John Moody, how robust are these magnets to neutron damage? And I assume he means the high temperature superconducting magnets.
Okay, that's a good question. So SPARC will have some shielding, about average about 10 centimeters or so of shielding, not a full blanket, not enough for not enough for a power plant, not enough to do breeding, not enough to protect the magnet, a steady state machine from running. But for SPARC, with the fluence that we expect, there should be no problem. We've actually done experiments with irradiating HTS with neutron sources and with proton beams, and up to the fluences that we expect, they should be okay. We're planning to do an experiment to irradiate them at low temperatures in a nuclear reactor, and we'll know more. But that's really more a question about what will the lifetime of an HTS magnet be in a full-size steady-state plasma power plant. So we think we're okay there.
Okay, and then there's a question from Andre Demi, who asks, does the high temperature superconducting parameter plot current density take into account the substrate, etc., or is it just the superconducting material itself?
Yeah, that's the superconducting machine itself. So we always talk about it in terms of when we talk about the critical current, it's an engineering critical current. It's not the critical current in the superconductor itself. It's the critical current in the whole ribbon. And that way we don't fool ourselves, because the substrate can, depending on which vendor you go to, the substrate can change thickness or size. But these things can carry a lot of current. A single one of those little ribbons, as you saw way back when, one of these ribbons can carry 1,000 to 10,000 amps, depending on the temperature. So extraordinarily high current densities in the actual superconductor itself. Superconducting is one of the miracles of science. Let's face it, that you just cool these things down and they carry electricity with zero losses. It's really a remarkable thing.
There's another question from John Moody. When will you get the first plasma?
We're aiming for 2025. That's the current schedule. It's pretty aggressive. It's only 4 years, but not that different again than what TFTR and JET did. And that, again, those were big government funded programs, and TFTR was 5 to 6 years, a little shorter for JET. As a private industry, we can move faster. I think some of it has to do with the risk you can take in the processes, but also things like the supply chain. Just to give you a concrete example, since I'm on the superconducting slide, it's very difficult to secure a supply chain when you're government funded, because every every procurement has to be done, on competitive bids. You don't establish any long-term relationships with vendors. That would all be illegal. But a private company can do that. It can say, look, we're in it for the long haul. Let's make an arrangement over 5 years to provide materials for you. And that can really help a lot in terms of how things get done. So there's a whole lot of reasons why we think we can go a little faster than say JET or TFDR did. It is ambitious, no question about it. But yeah, 2025, and we hope that we'd be putting deuterium in within a year of that, something like that. I'm sorry, putting tritium in within a year of the startup.
And there's a question from Chris Schroeder. Admittedly off topic, but if there's time, what are your thoughts on the implications this tech might have for global socioeconomic inequality?
Oh, that's a good one. I mean, if you're thinking about dealing with the climate problem, you have to think internationally, right? You have to be able to build plants anywhere. And we think that this, fusion is it's a nuclear technology, but we think it's much safer. It has no proliferation risks the way fission does. So it should be possible to deploy this everywhere. And one of the advantages of our pathway to go to these high field compact devices is that we imagine, and really our goal is that every component can be built in a factory and shipped to the site for assembly. So you don't do you don't do fabrication rather on site the way you would for some of the larger schemes. The EU demo, for example, is so large that the components could not be shipped. There's no road, there's no highway, there's no railroad that could carry the components. And it's very difficult to think how technology like that could be widely deployed, because how do you get the workforce that could do that kind of fabrication? And once you assemble the workforce, will they want to move on to the next place? So, to solve the world's energy problem, to make a dent in it with fusion, you're going to have to deploy thousands of these power plants of the arc scale. And that's really very widely deployed. And they're going to have to be in places where there isn't the kind of infrastructure to do advanced manufacturing. So being able to ship these components, put them in a ship, send them around the world. And again, it's the underdeveloped world where most of the energy growth, energy demand is expected. And so that's the demand you have to feed if you're going to solve the climate problem.
And Shing has asked, with the system getting smaller with HTS magnets, does the risk of disruption and heat loads increase? What are the mitigation strategies?
Yeah, as I said, when we analyze the disruption risks, we make a one-to-one comparison with ITER. Overall, I think we conclude that it's about a wash. You know, some things get a little harder, some things get a little easier. We're not using, our first wall is not going to be covered with beryllium, so we don't have that issue of a very low melting point material covering the first wall. So we think that helps us. We also don't have, because it's a shorter pulse machine, the first wall is passively cooled, not actively cooled. So the material of the first wall armor is, you know, thick. It's not thin layer with cooling water running behind it. So that's another advantage that we have. But you know, again, roughly speaking, the disruption challenge is similar. We're hoping this runaway mitigation coil idea works. That solves one of the really big problems. We think we can design the machine for the forces, the disruption mechanical forces, but the runaway damage and some of the thermal losses, those you can't easily engineer away. And we'll probably have a massive gas injection as another mitigation scheme as well. The nice thing about the mitigation coil is it's passive and it's triggered by the dIdt of the disruption. So you actually don't need to predict the disruption. You use the dIdt itself to energize the coil. So you know, that's an advantage as well.
So I think you might have already addressed this, but Bruce Cohen asks, where could you cite a DT device and how difficult will the licensing process be?
Okay, that's a good question. As I said, we're citing it at what was Fort Devens. It's now it's basically an industrial park in the western suburbs of Boston. Um, so SPARC itself is not licensed by the NRC. It's actually gets a permit from the state of Massachusetts. Um, there are a lot of states which are what they call agreement states, which means that certain facilities, nuclear facilities that don't come under the NRC are handled by the state regulatory agencies. And so SPARC would be regulated the way an accelerator would be, whether it's an industrial, like a medical accelerator or experimental accelerator. The big concern, of course, is tritium. The actual, we don't, you know, there's no meltdown. There's not the kind of dangers you have with a fission plant. So the big safety hazard is tritium. So you need to convince the people doing the permitting that you have a safe plan. And we actually have gone through the first round of permitting. So we think that's going to be okay. We have a pretty good relationship with the people in the state government that are doing that. So now when you get to SPARC, it's another step, and there's an very active group now. So the fusion industry people, plus the national lab people, plus the regulatory agencies have already started working on coming up with a new regulatory regime that would be specific for fusion. And that's a different approach than what they took for ITER, where they simply adopted the fission codes. And that's a difficult thing to do. And I don't understand the details, but philosophically, it means that um, you're the you have to sort of what you have to demonstrate is very different in that regime, and that makes it very difficult to bring a new technology up. And the people in advanced nuclear are running into that. They're finding it very difficult to get licenses for their new technology because there's no track record. There's a chicken and egg problem, and so we you know, again, there's a group of people working on trying to come up with a new regime which takes into account the differences in the technologies. And that seems to be going well. There's actually a meeting next week of the NRC with all the commissioners that are going to talk about this.
All right, so there's a question by Linda Destro, but I think it was already answered. And so I'll skip over to Brooke Marsh. How is the plasma heated? What is the efficiency like? Generation, coupling, etc.
Okay, yeah. It's ICRF, minority heating. Of course, it's actually a pretty hard problem to get a precise number on the heating efficiency, but the code suggests very high single pass absorption, 80 or 90% single pass absorption. So we expect the overall heating efficiency to be very high. You also get very good focusing because you're at 120 megahertz. We were successful on CMOD with this scheme, and other people have been successful too. Because of the higher field, we're running at higher frequencies, which means shorter wavelengths. And the device is larger than CMOD, so we'll get very good focusing of the RF waves. So we think that'll work very well. We have to design antennas that can take the power density. That's always a challenge. There's some black magic in antenna design and RF breakdown, but we have a lot of experience, so we're hoping that all works well.
And Faye Gonzalez asked, what materials are being considered for the walls to withstand radiation damage?
Well, that's a recent decision. We pondered over that for a while and decided to use tungsten. So all the first wall, everything that can see the plasma will be covered with tungsten.
And then Maxim Monsky asks, other than achieving its mission goal, Q greater than Q, is SPARC envisioned to provide important physics data for the fusion community?
Yeah, I think the answer is yes. So as I mentioned, that fast alpha physics is one. Another one, area that Maxime knows well is the diverter physics and power handling. The SPARC will be operating at a heat flux density which is prototypical of a fusion power plant. And so understanding the physics in that regime at high field, at high density, I think will contribute a lot to that understanding. And we have an alternate magnetic configuration that we'll be experimenting with, a long-legged diverter. It can run the Super X or the X point target diverter, and that's at somewhat reduced parameters. We have to lower the current to around 5.7 megamps to do that, but that still would get us Q above 3. So a high fusion gain with one of these long-legged diverters we think would be very interesting and we'll learn a lot from. And of course, we'll be extending the database in a lot of other areas as well, into a regime of higher field, higher density. But probably the plasma wall interactions and the alpha physics are the two big ones, I think.
Okay. Thank you very much again. That was a great talk, and enjoyed learning all about SPARC. And I invite everybody to meet yourselves again so we can thank our speaker again. And otherwise, I hope everybody has a great rest of your Thursday.
Okay, very good. Thank you very much for your attention.